In this video, we're going to learn about heating and cooling curves. So here's an example of a heating curve. Let's say that we have a sample of ice, and initially the temperature is something quite low. Well, as we start applying heat to it, the temperature will rise as the ice particles vibrate faster and faster and faster. And eventually, we reach a point where you can continue adding heat and the temperature doesn't change. Well, this is because this is being used to change the phase of ice. And what we can say is that instead of the heat being added causing the ice particles to vibrate faster and faster, which is what's happening until 0 degrees Celsius, instead of that, once you're at the melting point, the heat being added is used to break the hydrogen bonds that are holding the ice particles together. So they're not vibrating any faster, the temperature isn't rising. What's happening is the hydrogen bonds are breaking. But eventually, all the ice is melted, and then the formed water, well, that can start absorbing heat and moving faster as a result of this absorbed heat. And so that's why the temperature starts to rise again. Once all the ice has been melted and we're in the liquid phase, the liquid water will continue to absorb heat and have its temperature rise as the particles move faster and faster. Eventually, though, we reach the boiling point of 100 degrees Celsius, and again, the temperature just sort of levels off. As more and more heat is added, that simply causes the boiling to occur, causes the particles to separate from one another. And what you might note is that if you've ever put a pot of water on your stovetop, you might have it reach the boiling point when you're on the absolute highest setting, but you can turn it down a bit and it might still remain 100 degrees Celsius. The only difference is that the rate of boiling it lessens because you're just putting in less heat per second from the stovetop. Nonetheless, you're still going to stay at 100 degrees Celsius and the water still will continue to boil. Of course, after boiling, steam could get hotter and hotter still if more and more heat is added, and that's what we're seeing here. Um, all of these processes are calculable for the amount of energy required to make them happen. So any process that involves the temperature changing, meaning, say, this area here, or this area here, or this area here, anything involving temperature changing is going to require Q equals mc delta T, mass times the specific heat times the change in temperature. And I'll note that the specific heat of any substance varies depending whether it's in the solid, liquid, or gaseous phase. Now, when there is no changing temperature, when we're talking about a change of phase, we have to use a different Q. And that would be Q equals mass times the enthalpy of fusion or enthalpy of vaporization. Enthalpy of fusion is the heat change that is associated with changing from the solid to liquid phase or the liquid back to the solid phase. And heat of vaporization is going to be the heat associated with the change from liquid to gas or from gas back to liquid. Now, I'll note that these heats of fusion and vaporization, they may be expressed in joules per gram. They might be expressed in kilojoules per gram. They also might be in joules or kilojoules per mole. So you have to be very careful to make sure that you're using the appropriate the appropriate heat of fusion or vaporization to match whatever the problem is asking you or giving you. And another thing that's very important to note is that if we're talking about a change in temperature, well, the sign of delta T, whether it's positive or negative, will give you the correct sign of Q, whether it's positive or negative. Of course, any heating going from a low to a high temperature will have a positive value of temperature final minus initial, meaning that you get a positive Q, and any decrease in temperature will give you a negative Q. Of course, in the case of changing phase, if you just look up the value, enthalpy of fusion or enthalpy of vaporization, it's always going to be shown as positive. So what you need to know is that you should make your heat of vaporization or fusion negative if you're going sort of from a higher energy state to a lower. For example, if you're condensing vapor from the gaseous phase down to the liquid phase, definitely use negative H sub V. And if you are freezing a solid, use a negative, sorry, if you're freezing a liquid to the solid phase, use a negative value of the enthalpy of fusion. So let's do a practice problem. Calculate the energy released when 10.0 grams of water at 25 degrees Celsius is cooled to ice at negative 10 degrees Celsius. I always like to draw out a cooling curve in this case, simply to break apart, okay, what do I need to do? What calculations do I need? So if I know that we are at 25 degrees Celsius and we're in the liquid phase, I know that we're going to start off at some temperature, 25 degrees Celsius, and we go down, down, down as heat is removed. And we eventually hit 0 degrees Celsius, and that's when we start freezing. And that happens. And then we cool it to ice at negative 10. So right now we're at the freezing point, 0 degrees Celsius. We need to continue going downward as well. So we need to do a 3-part calculation. The first one, we're going to do Q equals MC delta T. And this is going to be, oops, come on. Q equals MC delta T. This is going to be equal to the 10.0 grams times the specific heat of water is 4.18 joules per gram degree Celsius or Kelvin. And so that's M times C times, and the final temperature minus the initial is going to be 0 minus 25.0 Celsius, which is just a temperature change of negative 25 Kelvin. And what this comes out to is negative 1045 joules. So that's our first step, our going from 25 degrees Celsius down to the freezing point. The next Q that we're going to be using is Q equals M times H sub F, the heat of fusion, because we're not changing temperature, we're simply freezing the water into the solid phase. So this is going to be equal to our 10.0 grams times our heat of fusion, which is 334 joules per gram. And since we are freezing, we should make this a negative 334 joules per gram. And so what this comes out to is that Q equals negative 3,340 joules. The third part of the calculation is another Q equals MC delta T. But this time, yes, we do have 10.0 grams, but we're going to use a different value of C because the specific heat of ice is 2.09 joules per gram degree Celsius or Kelvin. And our delta T is going to be negative 10 minus 0, right? Our final of negative 10 minus our 0 of our initial temperature. And so our negative 10.0 degrees Celsius or Kelvin will be our delta T. So the Q ultimately comes out to negative 2090 joules. And so now that I've got these 3 different steps, the total here is going to be negative 6,475 joules, which we will round according to there being 3 sig figs. It's negative 6,480 joules. That will be our Q for, again, the whole process. So I hope this video has been helpful. Please feel free to leave any questions or comments in the comment section below. Thanks for watching.